Next, we have Professor Abigail Bodner, who I think has a rather unique background mixture. She has an environmental science and applied math background. Her research focuses on the relationship between climate, physical oceanography, fluid dynamics, and turbulence. She addresses challenges in ocean-atmosphere interactions by adapting data science tools to the intersection of oceanography, climate, and computing. Professor Bodner, her bachelor's degrees, multiple ones, in geophysics and math, and then a master's in atmospheric sciences from Tel Aviv University. And then that wasn't enough, so then she got another master's in applied mathematics, and then a PhD in earth, atmospheric, and planetary sciences from Brown. She was a Simons Junior Fellow at NYU, and then she joined the MIT faculty in 2024, so just last year. She's also actually a co-founder of the Climate Match, which is the Climate Match Academy, which is an online program that has a mission to build a global and diverse climate science community. Please give a warm welcome to Professor Abigail Bodner.
All right, thank you, everyone. So I assume that a lot of people have seen figures like this at some point. As we're starting to think about how climate is changing, it's very common to look at projections of temperature into the future. So what we're seeing here is projected surface temperatures over the next decade. And the way this is done is that we compile all the observations that we've had since the 1850s, and that's that gray line shown on the figure. And then we use climate models from all over the world, and we initiate them using different emission scenarios. And we're doing that based on decisions that we're making today. So decisions that we're making today are going to impact the projected climate that we're looking at into the future. And we can see that there are different levels of surface temperature increase depending on red, blue, or green. And this is, again, related to the emissions level. And we're looking at anything between a few degrees of temperature to over 10 degrees of Celsius. So really a wide range. But it's really hard for me, at least, to understand what it means global surface temperature increase. But rather, it makes a lot more sense to think about how it's affecting us, in particular, in Boston. So a lot of us in this room have experienced several really warm summers over the past few years. We're seeing more extreme heat waves. You may remember the wildfires in Canada that are related also to increase in surface temperature, which resulted in smoke that was too thick to breathe. I was living in the New York City area at the time. I had to come pick my kids up from school because they weren't able to breathe. It was really scary. Increase in surface temperatures also means that the cold winters that we know in Boston, rather than having snow on the ground, we're now seeing flooding during the month of January. So that's also a little bit unusual. So we're seeing these temperatures increase. We understand that this is a trend that's going to become more and more extreme. But what it means by increasing temperatures is also means that we're increasing the heat in the climate system. Now, a surprising fact is that most of the heat is actually not contained in the atmosphere. So what we're seeing here, this is showing us the heat content in the climate system from 1960 until today. And in that red stripe, this is land, ice, and atmosphere combined, whereas the blue is the ocean. So what we're seeing here is that the heat in the climate system, 90% of it is contained within the ocean, and in particular in the upper ocean, which is those light blue colors over there. So in order for us to understand what global temperatures are going to look like into the future, the key for that really is understanding what's happening in the upper ocean and how the heat is contained in the upper ocean that's interacting with the surface temperatures in the atmosphere. Unfortunately, though, unlike the atmosphere where we have a lot of weather stations and satellites, in the ocean it's much harder to get measurements. So yes, we can measure the ocean surface, but if we want anything from within the water, we need something to physically go in the water and measure it. So whether it's people that go out to sea and throw things in the water, or these like ocean drones that are called gliders, or even some people take measurements with sea mammals, not me. But even though it may seem on this global map that we have quite a lot of measurements worldwide, the distance between 2 points that we measure could be hundreds of kilometers. Now, think about Boston again. That's not good enough if we're thinking about the weather, right? We need a much hyper-local understanding of what's happening in order to understand how the climate system is responding. And in particular for the upper ocean, just the way we see these heat events at the surface, the scales that are smallest are the ones that are determining the heat that gets transferred between the atmosphere and the ocean. So we don't really have the data that we need to understand this crucial problem. So what people normally do, myself included, is we use simulations. So we don't, this is a model. This is not an observation of the globe. But what we do is we take kind of our best understanding of the physics of the climate system and we code that up in a computer. And then we use that to simulate how the variability of the ocean can change. So this is an MIT model. It was developed in this building before my time. But it's one of the few global models that we have at a resolution that can really simulate what's happening in the upper ocean. So these scales are too fine to be resolved by the long-term climate projections. We need special models at a 50-time resolution than we normally have. So just to appreciate what these look like, hopefully this comes up on the screen, we've got a lot of very fast varying motions that are associated with atmospheric storms and winds. And then we've got the slower oceanic movements. And I hope you appreciate that these really change globally. We have regions where we've got very strong currents and very fast ones, others that are more quiescent. And it's really not enough to just think of things on the bulk sum, but rather we need to understand things on a more local scale. So I'm going to zoom in to one region just to get a better understanding. This is in the region of the Gulf Stream off the coast of the US. And what we're showing here, this is heat flux or heat transfer in the upper ocean. So these are one of the metrics that we can look at to understand how the ocean and the atmosphere are exchanging heat and carbon to determine these surface temperatures into the future. And this is what I'm considering the truth. This is given from this high resolution simulation in this smaller domain. And this is what the global models think this metric should be. So when we look at climate change into the future, these global models that we're using are assuming that this is how strong the ocean variability is for heat transfer. So we're seeing that we're way off in terms of magnitude, in terms of variability, and it's really not capturing what we can see from the truth of the high resolution model. So we don't have good models or good observations to understand this problem, yet we know that it's really crucial in order to improve our predictions. So this is what my lab is working on at MIT, is to try to compensate for these errors, to try to see how can we better understand the system in order to improve our projections into the future. So some approaches we've taken is to try to improve the theory at the very smallest scales, to try to examine certain laws of physics that are associated with these small-scale currents. Think about turbulence and all sorts of flow dynamics that are occurring at the smallest scales, and then go back into the global models and see what it does. So it seems to be doing a little bit better if we look back at these two visualizations. We're capturing more of the intensity. We've also started using AI in order to see if we can improve the predictions based on certain climate variables. So rather than telling the model what the physical law should be, we're letting the neural network learn this relationship between the large-scale climate variables and the heat flux. And again, this is looking much better now, right? We're starting to see a comparison that's almost one-to-one with what we consider the truth. Surprisingly, though, when we go back into these long-term projections to look at climate in the future, and we tell these climate models, look, here are better heat fluxes of the upper ocean, we can get widely different results between two different models that are simulating the same thing. So this is a comparison between two different global models, and this is the Atlantic meridional overturning circulation, which is related to the Gulf Stream. And what we're seeing is that better heat in the upper ocean is resulting in either a strengthening or a weakening of this exact same current in two different models. So there's no consensus of how the global climate will react to better captured heat. And what this has led me to understand is that we have a fundamental lack of understanding of how these multi-scale problems are really, the multi-scales in the ocean are really interacting. So how do the smallest ocean heat fluxes determine the long-term climate change? So looking into the future, we're trying to really come down to an understanding of how we can understand this transfer between small and large scales with the limitations of technology, but also trying to advance technology forward. So this is a new GPU-optimized simulation that, again, was developed here in this building. It's called Oceananigans. It has a great name. But the fact that it's more adaptable to new hardware means that we can push the limits of simulations to higher and faster than ever before. So we're developing a new model that's of the largest scale and highest resolution that's ever been done for the upper ocean, where we're able to really understand where is the heat going, where is the energy going, how is it being transferred across these different scales in the upper ocean, and then we'll be able to really improve our understanding of at least the physics at the smallest scales, to close that gap. We're also starting to think of how can we leverage different measurements of the ocean surface. So there are a few different satellites that orbit around the world and measure the surface temperature and salinity, which is the salt, and sea level height. but they don't always overlap in time and space, and some of them have gaps. So we're thinking of new novel AI methods to kind of fill in those gaps so we can get a comprehensive understanding of the upper ocean variability. And lastly, what I'm really excited about, and I'm having a couple grad students come in the fall to work on this, is we're thinking about how can we really bypass the computational challenge that's related to really high resolution but really long-term simulations. That's something that we really can't do at the moment, and it's crucial to understand how variability in the upper ocean is determining long-term climate change. So we're using AI emulators, which rather than actually simulating and telling the model which equations to solve, it's telling the model to predict the next time step. And we're able to do that much, much faster, which means that we can now combine high resolution and low resolution models that look both at long-term and short-term in order to really understand how the variability and the heat fluxes in the ocean are going to change over time. So that was probably more complicated than can be understood in this short talk, but what it's going to allow us is going to provide us a tool to answer some of these fundamental questions that we still don't understand. So going back to thinking about these long-term projections of climate change, we usually use this one metric of sea surface surface temperature, but I hope you all can appreciate now that it's a much more complex problem. It's really not about one metric. It's not about the global sense, but rather it's the local scales that are the ones that are determining it, both in the atmosphere for extreme events, but also in the ocean in terms of how we're taking up heat and then feeding back onto the atmosphere. So with that, I'll finish. Thank you.